one thing I would like to remind you guys is that the due date for the homework 1 is today, okay? So please remember to turn it in, okay? And I also have the TA posted homework 2 on the EE class. So if you have not, it's probably a good idea to check it out tonight, okay? Okay, so, okay, so back to the last topic of today, okay, which is the range tree. What is range tree? Okay. Remember we talked about one-dimensional range query, right? One-dimensional, at the very beginning. This 1D range searching algorithm, right? So this 1D range searching algorithm is very nice, right? Okay, if we can generalize that to higher dimension, wouldn't that be nice? Right? Okay, but the issue is how? How do we do that? Right? How do we do that? Because obviously, like when it comes to the higher dimension, like the location of the point is not only determined by one coordinate, right? So that's exactly like where the range tree concept comes from. Okay, so query is actually in the range tree. Query is processed one coordinate at a time. So when I say that, I'm actually using the one-dimensional range query to do this query processing. Okay, which is nice, right? But what is the data structure that allows us to do that? Okay, so we are going to have one balanced binary search tree for each coordinate. To be honest, it's much more complicated than that. Okay, if there are more dimensions, okay, a node is associated with another balanced binary search tree for additional coordinates. When a node here, okay, actually refers to all the internal nodes. Okay, any internal node. Okay, to be exact. Okay. So for the last coordinate, okay, the node stores the point information. Okay, so we don't actually store the point information, everywhere. We only store that in the last coordinate, in the binary search tree of the last coordinate. Okay, so if you look at the two, let's use 2D range tree as an example. I mean, if you can understand 2D range tree, you can understand the high dimensional range tree. I mean, just like what we did for the KD tree. Okay, so we know that. Okay, we know that. Okay, in a binary search tree, each internal node will be a root of a subtree, right? Each internal node is actually a root of a subtree, right? Okay, so it, of course, like we can assume this is the we have this binary search tree for the x coordinate. Remember, I mean, here we're talking about like 2D, right? So we have x coordinate, we have y coordinate, right? Okay, so the thing is like this. Okay, look at here. Okay, assume these are the points. These are the points that situated, under this subtree, rooted at least internal node. So this internal node not only serve as internal node, it also has a pointer. He has a pointer that points to another binary search tree. Okay, and this binary search tree, this one, okay, it has the same set of points like this. Okay, it has same set of points like this. But this one, these points are sort of sorted by x coordinate, right? Right? Because the whole thing is a binary search tree sorted by x coordinate, right? But here, okay, here, this binary search tree when they store these points are sorted according to their y coordinate. Okay? And you have that for every node, not just for one internal node, but for every node. Okay, every internal node. When you have a pointer that points to a binary search tree, something like that. Okay? So the basic idea is like this. Okay, let's assume we already have this data structure. Let's assume we already have. Let's just let me just keep but I mean this try to make sure you guys have fully understand or full understanding of this data structure. Okay. What I mean is like this, okay? For example, okay, this is the original, the binary search tree that is sorted by x coordinate, right? And as I said, you have, for every internal node, there's a pointer that points to another binary search tree. Okay, for example, I mean, if this is a node, okay, and the points here, okay, will appear here, but they will be sorted by y coordinate, right? Remember I told you, right? Okay, and you have that. I mean for every level, Okay, so think about this. You actually also have a binary search tree starting from the root. The root will store all the points, sorted by x coordinate, right? And the root will also have a pointer that points to all the points sorted by y coordinate. I will get to that point later. Yes. So, okay, once you get the understand the idea. So how do we do a search? Okay, think about this. Okay, it is not very difficult. Okay, to find the points because we are doing the rectangle range query, right? So we know like exactly the range for x coordinate, right? And we know the exact range for the y coordinate, right? So we can use the x range to find the points that fall into that range, the x range, okay, in this binary search tree very quickly, easily, by means of the 1D algorithm. Remember we covered that already, right? Sort of, right? We covered that. And obviously, like we search for two ends, right? So anything that for, if a complete subtree needs to be reported, we report that, right? Originally for 1D case, right? I mean, and for the end point, when we reach the leaf node, we will check if that point fall into the range or not, right? Okay. Now, okay, because we cannot just report all the points that fall into this x coordinate range. Why? Because some of those points, their y coordinate may not fall into the y range, right? Right? Because now we have X range, we have range for Y as well, right? Okay, so now, okay, of course, for the endpoint, because it's 1 point, right? It's 1 point, and we can, we can check if that point, okay, is X coordinate and Y coordinate fall into the right range or not, right? That doesn't take more than constant time anyway, right? Right? If it's like a leaf node already. The issue is, remember, like when we need to report the points under complete, all the points in the subtree. How do we do? Okay, remember, for example, like say, when we need to report these points in this whole subtree, originally, because all these points, their X coordinate fall into the range. Now, we cannot report all of them. We need to check, right? We need to check if their Y coordinate fall into the range or not, right? Well, no, we only have the points that has a valid X coordinates here, right? Now, we just use the same one-dimensional algorithm to check if their Y coordinate fall into the Y range or not, by using basically a similar concept, similar algorithm. Again, you search for two ends and report all the points that fall into this range. Okay? So the range tree basically is the concept is very, very straightforward. Okay? So what's the catch? Yes?
There's a lot of concepts.
Yes, what?
Why is there a lot in the storage capacity?
What? Log n.
Yeah, log n.
Oh, you mean like yeah, I'm going to get to this point.
Okay.
I'm going to get to this point. Yes, that's a good question. Yeah, but so what's the catch? Remember, we have to pay more price for the storage. Remember, originally, in the KD tree, the complexity for the storage is linear, right?
Yeah.
But now, remember, here, okay, we have to pay more price for the storage. Why? Think about this. Each internal node, you will have to, store all the points, under here, here, but in a different order, right? Okay. Actually, like you can imagine, the node here, all the points stored here, okay, they actually, appear already here once, right? And same thing, the nodes appear here, actually appear here and here as well. Okay, so you can imagine each level. Let me use a level. Okay, this level. Remember, I told you the root. I'm sorry. Where's I'm sorry. Yeah. The root. Okay. Has a pointer that points to all the points that store the points in y coordinate, right? So each level, okay, actually you will find, a tree or a set of tree that basically store all the points. Okay, the second level we have two branch, right? Those two children from the root. Okay, each one represent like a half of the points, right? Right? Each one cover half of the point, and each one will have a pointer to point to. So it's going to be something. Where is my? Okay, remember the root. It has a pointer to point to another tree. So this one will be identical to this, right? Not only that, okay, this one will have two children, right? So this child, it has a pointer to point to subtree. This one has a pointer to point to another tree. And assume this part will be the nodes covered by this subtree. This will be the node covered by this subtree. Okay, so this part will be covered here. This will appear here. So the combined will be all the points again, right? So this level, we have this one, cover all the points. The second level, we have these two trees that cover all the points again. The third level, we have 4 nodes, right? And you will find like each node will point to another smaller tree. And the combined, again, will cover all the nodes, right? So basically, okay, you have data structure, okay, linear data structure for pretty much every layer, right? How many layers do you have? Log n. So the total will be n log n. Yes. Yeah.
Why not we use the Y tree?
We use what?
We use the Y tree.
It's not as easy. It's not as easy. Because think about this, you say we want to reuse this part at here, right? How do you use it? Because you need to distinguish. I mean, each node. For example, this node appear here, so you need to if you don't want this node to appear here, or you don't want this tree, then you need to have a marker here, right? If you count the complexity of the marker, it will be exactly the same as this one anyway. You're not saving anything. You're not saving anything. Okay? So the query actually is very straightforward. Okay? Once you understand one-dimensional range query, you basically apply one-dimensional range query more than one time. You can see that, okay, for example, you start from the beginning, you can see, okay, basically the whole thing, the structure is similar to one-dimensional range query, but the only change is that, okay, this part, okay, originally in the original place, we report all the points here. Now, we'll call 1D range query on the associated tree with a Y range. The other parts stay the same. Okay, the other parts stay the same. So, so think about this, okay? So how much time does it take? Because basically, it takes the amount of time, like basically you are trying to find the two ends and then report all the points in between, right? Something similar appear here, okay? So the query time, okay, the query time, still going to be n squared, log n squared plus k. Why is log n squared? Okay, because it's going to be log n times log n, because you have, you're going to have here. And for each level, you may need to do 1D range query again, right? So you may, in the worst case, you may do this one, okay, this one. So the query, okay, this path will take log n, right? You have log n number of internal nodes, but each one of them will have to do this again, right? In the worst case. So it will be log n for each of them. Okay, it's bounded by log n. Okay, so it's going to be log n times log n. Okay, so it'll be log square n. Okay, basically, and then of course you need to account for the points that you have to report. So it'll be log square n plus k. Okay, think about this. The same idea can be applied to d-dimensional. So it's just like, for example, here. Okay, for all the internal node, you just have a pointer to point to another tree. Okay? And the query will work exactly like that. You deal with one dimensional at a time. So it's going to be log n times log n times log n plus k. So think about this. Well, obviously, I mean, this storage complex is more expensive, right? Because originally, I mean, the KD tree only used linear storage. Now we use n log n, right? But the complexity original is like, it's going to be n to the power of 1 minus d over 1, right? Plus k. I remember it's something like this, right? That's time complexity for the KD tree, for the query, right? Now it's going to be so this one, no matter how big this d is, it is smaller, still smaller than a fixed fraction of, n to a power of fixed fraction, right? So we are trying to reduce the order for the query. Okay, so it's like we are sacrificing more storage space to exchange for like a faster query time. Okay, and so we have all this benefit, right, for the range query. One thing I haven't really discussed: how do we construct it? I mean, we need to construct it efficiently. I mean, of course, like once I tell you how it looks like, everybody can construct it. I mean, but how quickly can you construct it? Right? Because think about this. Okay, I mean, for every internal node, okay, then you need to sort of like do we need to sort all the points? And then, do we need to put these points? What should I say? Like, build this binary search tree, build this binary search tree separately. If you build the binary search tree separately, it's going to cost you, a lot for the construction. Okay. So here comes the basic idea, okay? Well, the idea is like this, okay? Something similar to what you want to achieve, but it's not exactly like that, okay? You don't reuse this one for the next one, but you can reuse the order here for the following subtree. Okay, what I mean is like this, okay? Remember I told you, okay? Remember I said like, okay, there are two ways to construct a binary search tree, right? One way is to insert each node separately. Another way is to sort the numbers first, and then you just put them in the right order, that's it, right? Because you can use array to do the job, which takes, I mean, it's very quick. The construction only takes linear time, right? The sorting takes n log n, obviously, but the construction only takes linear time. So basically, okay, starting from this, of course, we have to solve the whole thing by using x coordinate, right? So this will take n log n, obviously. And then the next thing, we are going to solve all these little points by y coordinate. Okay, and then of course they will take care of this subtree, right? I shouldn't say subtree. I mean that tree, right? Because we already saw the points by y coordinate, so we can put those points, in the right order to make it a binary search tree, right? And then, okay, here's the thing, okay? For the next level, we know there are two subtrees, right? Okay. We prepare the array here. We prepare the array here. And then from the value here, we know exactly what how should I say? What node should be put in let me see. No. Okay, no. Because we already have all these points sorted, right? This node sorted, this point sorted. So we start from we look at the y coordinate. We start from the smallest x. Because they are already sorted in y coordinate value, right? So we just look. We just do it one by one. Okay. Okay. Starting from the smallest y value. Okay. We check. Based on the value here. Say if the let's give it a value. Say this value is 50. Okay. What happened? One moment. Okay. Say this is 50, okay? Say we have a 50 here. Okay? This is x coordinate value, right? The largest x coordinate value in this subtree, right? Right? Remember the original 1D tree, right? So
not the largest, it's the middle.
no, the largest one on the left subchildren. Oh, yeah, you are right. Largest value from here of this of the left child of left subtree from this node from the root. Okay, from root. So for each point we already sorted in the y coordinate, right? According to y coordinate. So we check. Okay, so we just check it one by one. Okay, we check the x coordinate value. Okay, if the x coordinate value is smaller than 50, we put it here. If it's larger than 50, we put it here. You just do it like in linear time. You can put them in the right, in the right tree, right? Basically, you just take like some, each node you just do one comparison. You know exactly which tree to put it, right?
50 is assigned to the root, right? Not the thing.
Assigned to the root. What do you mean by assigned to the root?
We compare this node with the root, right?
Compare this node to not to the root, to the left child of the root.
Why? We have to write them.
Oh yeah. I'm sorry. Yeah, 50 should be here. 50 should be here. It's the largest value from of the left subtree. So 50 should appear here. Give me 1 sec. Okay, so 50 is here. I wrote it in the wrong place. Yeah, does that answer your question? Okay, so we just check it. We just compare with 50, and then we know exactly where to put each point. Okay, basically just put those points according to their y coordinate value, from smallest to largest one. And then you just compare each point their x coordinate value with this value here. You know exactly where to put it. So you can construct the second level in linear amount of time, right? And for the third level, you can do the similar job, and you can just put those points, in linear amount of time. And for each level, you basically just do it in linear amount of time. Okay, so that's why, okay, in 2D we require n-log n storage. I already explained what n-log n storage means, right? It's not too difficult to understand. And n-log n time. How do you get it done in n-log n amount of time? Yeah, you do it layer by layer, and you only solve it twice. That's the key point. You only solve it twice. Okay. Yeah. So I will not go into the detail of this. Okay, I mean you guys can read this yourself. Okay, so the complexity analysis. Okay, for the 2D case. Okay, it's going to be this much. Okay, so the complete theorems here. Okay, and which include the storage and construction complexity. And then, okay, again, for higher dimension range tree, okay, it actually, use this much storage, and it can be constructed in this much time, okay, and we can report the points that lies in the rectangle region using big O log n to the power of d plus k, okay, where k is the number of reported points. I mean, if you're interested in the recursive formula, okay, so this is the amount of time that takes for the construction of the tree. This is the amount of time that takes for the query, without counting the reported point, okay, because reported point will be another k, okay. Here this is the amount of time it takes to find the two end, okay. And you can obviously solve this recurrence relation to get the complexity above. Yes?
The rectangular query range, the term means that for 4-dimensional space, we can query to 3-dimensional query range.
I don't get your point. I mean, can you describe it again?
I don't understand the rectangular query range. What's that mean?
Rectangular range means like, for each coordinate, you have a range. Okay, so if it's d-dimensional, you have d range, which, is it good? Okay, good. Okay, so obviously, I think a lot of if you go to, some programming competition, I mean, some of this idea can be applied, obviously. Okay, and we have outlined the solution to solve this problem, but we haven't really talked about the degenerate case, because remember, we assume each node, their x coordinate and the y coordinate are different. Okay, because remember, in the KD tree, when we draw this vertical line and the horizontal line, no line actually go across more than one point, right? Yeah, but obviously it could happen, right? It could happen. I mean, of course, we don't really need to worry about, for example, in 2-dimensional case, like 2 points, their x coordinate, y coordinate are the same. then we don't need to worry about the same point situation. For the same point situation, as I said, like at the beginning, we just treat it in a, we just deal with it in a, using like a multiplicity number. That should do it. Okay, but if you have more than one coordinate, you could have some coordinate to be the same, but still represent different point, right? 2 points can have the same x coordinate, but with different y coordinate, right? So in other words, put it another way, I can have a horizontal line, that go past 2 different points. That's obviously possible, right? Okay. Not to mention, in the range tree, if you have 2 points stuck together, what do? Right? So so originally, we assume, in our discussion, we assume every coordinate, okay, there's no 2 points with the same coordinate for any coordinates, okay? But now let's take into account this situation. Okay. So we will treat each coordinate of a point as a composite number. What do we mean by a composite number? For example, if a point P, okay, its coordinate is Px, Py, then its composite coordinate will be Px bar Py and Py bar Px. Okay? And then the sorting of points will be done by looking at the values in composite one by one. So for example, when we compare the x coordinate, we will compare the first component first. If they are the same, we compare the second component. Then no 2 points will have the same x coordinate or y coordinate, right? Unless what? Unless these 2 points there, all their coordinates have the same value, right? But as I said, like we don't need to worry about that situation. No 2 points will have the same composite value, as long as no 2 points have exactly the same coordinate. Okay. So then okay. Of course, once we convert the problem, okay, convert the points, the coordinate into this composite coordinate, we should also convert this range query into a different format, right? The range query is like for example, like there's a range, right? Now we have to carefully read it, because what I mean is like let me just use one coordinate. Say this is 1, 2. This is 1, 5. This is 1, 10. Okay, and then we have a 1, 20. Okay, assuming the range is something like this. Sorry, my drawing is very poor. The range is of x range is from 2 to 10, something like that. Okay, and y say the range of y is from 1 to, say this is 10 as well. Sorry, yeah, 1 to 10. So 1 to 10, something like that. So how do we convert it?
We use the same convert.
Yeah, so this point will become, okay, this point will become 1, 2, 2, 1, right? Okay, this point will become 110, 10, 1, right? Right? So we will, okay, so here, okay, we are going to represent our X range by, you know, let me see. I made a mistake. I made a mistake. Ah, terrible. Ah, 5, 1. What am I talking about? Let me repeat. 1, 1, 5, 1, 10, 1. And then this is okay. So this point will become 1, 1, 1, 1, obviously, right? This point will be 10, 1, 1, 10. Right? So the range for the x coordinate will be from this 1, 1 to 10, 1. Okay, and look at here. Okay, it's important because, okay, you can see that this is 21. Sorry, 21. The 21, okay, 21 is bigger than 10, 1, right? When you look at the first coordinate value, right? It's bigger than the first coordinate, the first component of this x coordinate, right? So it's bigger than this one. So we know this one is out, right? But for this one, inside this range, okay, it's going to be 5, 1, right? It's going to be 5, 1. So you can see that this 5, 1 is actually between 1, 1 and the 10, 1, right? So there's no problem. It falls into the range, right? So when you do this conversion, okay, you know you can convert the original question into an equivalent question. But no, you don't need to worry about the same coordinate issue. Okay. By the way, in the homework, I actually prepared a question for you to try to see the equivalence between these two questions. So I want you to take a closer look at this thing. Okay. So that's pretty much about it for today. Any question? I mean, I just want to remind you guys again, the deadline for homework 1 is today, midnight. And the due date for the second homework, which has been posted to the EE class, will be due 2 weeks from today. Okay, the second coming Wednesday. Okay, so if you have any question, of course you are more than welcome to ask TA. If TA doesn't understand, I mean, maybe ask me. Okay, because TA doesn't necessarily not all TA take this class actually. Okay, they can do the grading, but probably not a good one to ask question to. Okay, so I guess that's about it. Any question? If no question, let's call it a day. Okay, thank you very much.